Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So, we are talking about design rule number 3, where we are talking about exact constraint design. So, what we are trying to say, never over constrain, do not start the fight, just concentrate on exact constraint design and we will have a very good design. So, first we will try to understand what is exact constraint. So, what you see here, a rigid body in 3D space, and what we realize that it has total 6 degrees of freedom. So, 3 translations, which is x, y, z motions. So, it can translate in all the 3 directions x, y and z, and 3 rotations, which is theta x, theta y and theta z. So, these are total 6 degrees of freedom one rigid body can have in 3D space. So, once we start with this, so what we realize that when we see this kind of configuration and we want to design a kinematic connection or kinematic clamp, many times it is a call. So, what we see here that there are 2 different kind of patterns like in top plate and bottom plate. So, in the bottom plate what we have is one tetrahedron hole and one V groove and then of course, the flat surface here. So, when a sphere 1 comes in contact with the tetrahedron hole here, it makes 3 contact. Similarly, when sphere 2 comes in contact to the V groove, it makes 2 contact, and when the sphere 3, when it comes in contact with the flat surface, it will make 1 contact. So, what we realize that total number of contacts here is 3 here plus 2 and then plus 1 here. So, total we have 6 contacts and later we will learn about it. So, if it is exact constraint design, so each contact will remove 1 degree of freedom. So, as we said, there are total 6 degrees of freedom for any rigid body in a space. So, if there are 6 contacts made and if it is exactly constrained, what we realize that it will be fully constrained. So, here once they come in contact with each other using this ball and 3 spherical contacts with the tetrahedron hole, 1 V groove and 1 flat surface, it will be completely constrained and it will not move, and that is why many times it is referred as a kinematic clamp. So, when if it is defined precisely and if we is exactly constrained, what we also realize that it always returns to the same location. So, the location of the object, so in this case the top plate with respect to the bottom is always defined, no matter what, whenever they come in contact in this way, it will be precisely defined and it will be always going to the same location, and that is how is possible to achieve very good repeatability in this case. Of course, the accuracy we still have to see if there is any deviation, but the repeatability will be ensured even if the parts are not precisely made. If the tolerances are not there, the tolerances in the parts in the making holes, if it's not, even if it's not defined and well, or if there is a error, the repeatability will be still ensured. The accuracy, yes, we have to see and we may have to adjust later. So, that is the point we want to make here, that if it is exactly constrained, the repeatability ensured and no precision dimensions are required. So, these are two examples. So, in the first one we have this 3 contact. So, a spherical ball with the inner tetrahedron hole, and then we have the V groove, and then we have the flat. So, it is the same 3 plus 2 plus 1. So, total 6 contacts. Yes, we have to check whether it is exactly constrained, and yes, we will learn how to calculate and try to learn how to find if there is any redundant constraints. But if it is exactly constrained, then it will be fully defined, and there will be 6 constraints in this case. In the second case also, so here the spherical ball is there, in the second example, what we see here, the spherical ball coming in contact to the V grooves. So, each spherical ball in a V groove, they will make 2 contacts. So, there are 3. So, 2 plus 2 plus 2. So, again they are making total 6 contacts, and in a way they provide 6 constraints, and if it is exactly constrained design, then it will be again fully defined, and no matter how many times we remove the part, but whenever we put it back, it will always go to the same location. So, again the repeatability will be defined. It is not dependent on the precision or the tolerances of the individual parts, even though even if the parts are less precise, but the repeatability will be still ensured. Yeah, so we will be learning about many such examples, and there will be modules where we wanted certain degrees of freedom. So, out of 6, maybe 1, 2, 3 or 4 or 5 degrees of freedom will be required, and we may need to constrain few. So, 1, 2, 3, 4 up to 6, and then we will take those examples and try to understand, and if there is any over constraint, in each case how to remove that or how to identify that. So, one of the way to understand it well is to first consider the 2 dimensional case, the planar case. So, we will try to understand more the exact constraint design in 2 dimensions. So, if we take the planar case, so just consider a plane, a blackboard or the top surface of the table, and suppose if we restrict the motion on the planar surface itself. So, that is why we call 2D motion or planar motion. So, if we restrict ourselves to this kind of motions, what we realize that there are only 3 degrees of freedom, and what are they? So, 2 translations x y. So, for instance, here x and y. So, any object if we put here on the top of the surface, they can move in x direction and y direction, and they can also rotate in the z direction, theta z. So, these are the degrees of freedom when we consider 2 dimensional case. So, if we provide a constraint or any contact, what will happen? So, first we would like to define a constraint, and what it says is a point of contact. maintained by a nesting force. So, there is a nesting force concept here. So, nesting force is some force defined in a so that the contact is always made. So, all these analysis is valid only if the contact is there. So, if there is no contact, then it is invalid. So, what we always assume whenever we are doing this analysis, that there is enough force, enough nesting force, so that the contact is always there, and so that we can do the analysis and can tell whether it is a exact constraint design or not. So, there is a concept of nesting force, and what it says, wherein the nesting force vector, so the direction shows here, goes through the contact point and normal to the surface of contact. So, for instance, if we check this, the contact will be somewhere here, and of course, then so this is the normal plane we have, and so this will be the reaction force. So, and to the contact. So, if we just rotate it and try to see, if this is the plate we are talking about, and suppose this is the post which is fixed to the base. So, this is the contact point we are talking about, say C. So, in this case, the normal plane, the tangent plane is passing through the contact point, and then normal to this is the constraint line, and this is the your nesting force we call it, and this will be the constraint, and this will be the force, reaction force. So, what we say in this case, it is a constraint. So, there is one point contact. So, in this case, if it is x direction, so it is a constraint along the x direction. So, it cannot move along x. So, with one constraint, we have one. So, this one constraint in this case is along x axis. So, it cannot move along x direction as long as the contact is there. So, constant is 1. What about the degrees of freedom then? So, what we find that it can still translate in y and rotate about z direction. So, if you try to move along y direction, if we give this motion, it can still slide. So, that translation is possible. If you try to rotate along the z direction, this theta z, so it is a perpendicular, and suppose, so it can slide here at the point of contact. So, it means it is possible to give that rotation z also. So, it is very easy to see if we just check this figure. So, this is the post, and this is the contact, and this is what now we are saying, this is x direction and this is y, and this is the z we are talking about, theta rotation. So, if we try to do, if we just put a normal at the contact, what we say that at the point of contact, since the displacement or what we are talking about is tangential to the constraint direction, it will not provide any kind of constraint there. So, what we are talking about is the instantaneous motion. So, at that instance, if you are trying to rotate, there is no constraint provided in this direction, and therefore, we cannot stop the rotation. So, therefore, we will have one rotation, y translation, and one rotation which is theta z rotation. So, total 2 DOF we have in this case. Of course, we are considering only 2 dimensional case, so we should be aware of that. So, in planar case, if there is one contact, there will be one constraint and there will be 2 degrees of freedom, and we should be able to identify. So, it is independent of how we choose our references, our coordinate system. So, be aware of that, and we should be able to find what kind of motions it can have. So, yes, I think I can simply wipe it out, and yeah. So, what we see here is the constraint we are talking about, which is 1, which I explained already, and the DOF, which is 2. So, already explained. What happens when we have 2 contacts, 2 posts? So, now we have 2 posts. So, if we try to define, this will be the contact. So, call it C1 and C2. So, in this case, the normal to the contact. So, it will be again x direction, but then these are the constraint lines. So, I am using different terms. So, we will talk about these terminologies again, but these are the lines along which the constraints are provided. So, it cannot move along this line. So, the constraints are provided along these 2 lines. So, what you see here is 2 parallel lines. So, if we just look at this object and then we try to create these 2 posts, C1 and C2 here. These are 2 constraints. So, what will happen in this case? So, yes, both the constraints are in the x direction. So, what will be the resultant effect? Whether there will be two constraints, but both are in x direction. So, what will happen? So, we will try to see. So, what it says, if there are 2 constraints which are parallel, and if there is a offset between the 2, what you realize that actually it provides the rotational constraint theta z. Because if you try to rotate along z direction, it will. So, suppose if I apply a rotation like this rotational moment, it will try to press this and or try to lose contact here. And if we make sure that the contacts are always there, the nesting force what we were talking about in the beginning, if there is enough nesting force that the contacts are always there, it means it should not rotate. So, the constraints here will be 1 in this case, and that is the rotational constraint, which is theta z. So, that motion will not be there, the rotation will not be there. What else? There will be. So, what about the x motion? So, if we try to move in x direction, right, x direction, of course, again that is not possible. So, there will be one more constraint, which is translation. Of course, the constraints are all in the x direction. So, they will provide translation constraint x. So, total 2 constraint, and if we go by the similar analogy, there are 3 degrees of freedom in planar case. So, 3 minus 2, so there will be 1 DOF. So, DOF will be 1, and what is that? So, if we try to move in the y direction, there is no constraint provided along this direction. opposite to this. So, therefore, it is possible to move in y direction, and therefore, if we talk about degrees of freedom in this case, then this is the translation in y direction. That will be the degree of freedom. So, one contact, one constraint, 2 degrees of freedom, 2 contacts, 2 constraints, we have 1 degree of freedom. But the way how we place the constraints or the contacts, I think that will define how we will remove the degrees of freedom, or how the constraint will be imposed. So, in this case 2 parallel constraints means it removes 1 rotational constraint. So, always remember parallel constraints, parallel translation constraint always remove rotational or rotational degrees of freedom. So, it will provide rotational constraint perpendicular to the plane, and of course, it is applicable to planet case only. What happens if we change the configuration? So, now in this case, so we have C1 which is along the x direction, and other is C2 the contact which is along the y direction. So, if you again try to analyze, so one post here C1 and then another here C2, C2. So, these are the constraints now defined along C1 and C2, which is along x and y. So, of course, they will remove that constraint, that degree of freedom. So, in this case, when we are talking about the degree of freedom and constraint, so one contact along x, one translation, x, and it also put constraint in y direction. So, total 2, 1 plus 1, 2 constraints now. So, again 3 minus 2 equal to 1. So, 1 dot should be there, and what is that? So, many times I think that will be always, if you are not careful, you may realize that putting 2 constraint in this fashion can constrain put a planar constraint, but it is not true. So, what is left is the rotation theta z, right. So, what will happen? What happens if you try to put any kind of moment theta z, or in case m z, if you apply, so torsional moment. So, what happens? So, the 2 constraint lines, if you extend, what you realize that they intersect at a point, and if you try to rotate along that axis, what will happen? If you drop the perpendicular to the contact point, what you realize that it can slide easily along that interface. So, at C1 and C2 both, because the motion there, the instantaneous motion, if we try to rotate, if we try to apply a moment along z direction. So, if there is any instantaneous motion, and because of that theta z, there will be translation at the points which are tangential. So, it is a perpendicular, and therefore, those particular this C1 and C2, it cannot provide constraint to that rotation, and therefore, it can rotate at that instance. So, always remember whatever we are talking about in this course is always about the instantaneous motion. So, if we try to rotate, there will be no constraints provided, and therefore, it can move. So, we will have that degree of freedom which is rotation z. So, in this case, this body, although we have two constraints in the perpendicular directions, but it can still have that rotation. Moving further, if we just increase the number of constraints, so C1, C2, C3. So, what we realize here is one along x, and there are two constraints provided along y. So, now what we are talking about is C1 along x, and there are two constraints here, C2 and C3. So, yes, it can constrain only along the normal, and what we realize that with each constraint there is making two instantaneous center of rotations and two parallel lines. They will make another instantaneous center of motion, which will be at the infinity. See. So, what we realize that, yes, for x motion we have C1, for y motion we can say C2 and C3 are there, and C2 and C3 together can constrain theta z rotation also. So, in this case it is a fully constrained. So, x translation, y translation and theta z rotation all constrained. So, therefore, in 2D case what we can say that if we put this post or contacts in this way, it will be fully constrained, and what we also realize that the plate has a single unambiguous position in 2D space. And what does it mean? So, it is a well defined. So, every time we try to place the plate against these three posts, it will always go to the same location. So, again the repeatability will be very high in this case. And coming to the constraints, of course, we have three constraints and degree of freedom is 0. So, yeah, we also know from the analysis that all the motions are now restricted. So, there is no planar motion possible. So, it is a 0, or 3 total in planar case we have 3 degrees of freedom, 3 constraints. So, 0 degree of freedom left. So, we can talk about many examples. Take a pause. Stop. So, we will take some examples here. So, for instance, take this case. So, there are two posts. So, contact C1 is made there and C2 against the two posts, and this is the object we are talking about. I think what we first need to understand is, so any object, any irregular shape if we take, and suppose if you are defining a contact here, so you define a post here and object. Always remember this is there will be a contact. So, C, call it C. So, C for contacts and C for constraints also, constraint line later. So, what you see here that we try to find first the tangent plane. So, this is the tangent plane, tangent in 2D case is a tangent line, right. So, the constraint will be always perpendicular to the tangent line, so and passing through the contact points. So, this is the constraint line. So, any motion along this line is not possible, but any motion along the tangent is possible, because it does not provide any constraint, and so be aware. So, this is tangent and this is the normal line. And this is the constraint line. So, be aware of this. So, if we go by this analogy, this example, so in this case these are the tangents line and perpendicular. So, we just try to construct so perpendicular lines. So, these are the normals and therefore, these are the constraints. So, because of C1 this is the constraint, because of the C2 this is the constraint. So, what it means, it cannot, the object cannot move along C1, line C1 and cannot move along this line C2, not possible. So, it means in a plane, if there are two, any plane if we consider, and if any two motions not possible, we can always find that it is not possible to move in the two perpendicular directions. So, say call it x y. So, it cannot move along x and y directions. So, the translations along both. So, suppose if I define a coordinate system x and y here, we can always resolve and can say that the translation along x and translation along y is now restricted. Of course, what we assume that there is a enough nesting force in this case. So, nesting force is there, so that the contact is always there. What is left is the rotation. What happens to the theta z? So, if we, so at the intersection, if we just assume a line, perpendicular line passing through the intersection point in the plane, and it try to rotate, what we realize, since it is a normal, so there will be tangential motion possible because of that theta z, and therefore, theta z motion is possible. So, this is the DOF, this is the degree of freedom what we have. So, the constraint is two constraint x plus y translations and DOF is 1, which is theta z rotation. So, be aware of this. Take similar example here. So, now we have C1, C2 and C3. What will happen in this case? So, yeah, it is a very symmetric design. So, along the C1, right, along C2, what we find that if we make the, so these are the tangent lines and these will be the all perpendiculars. So, C1, C2 and C3, these are the constraint lines. So, 3 constraints we have. Now, they are all intersecting because of the geometry of the object, and what we realize that one of them is redundant because it is not providing any additional constraints. So, for instance, C 1 and C 2 already constraining your x and y translations. So, if we take any pair C 1 C 2 C 2 C 3 or C 3 C 1, actually they are providing the same constraint x and y translations. But when we talk about the theta z, actually if you try to rotate along an axis passing through this IC where they are intersecting, but we realize none of them provide any constraint because all are tangential and it can rotate. So, in this case the constraint is, although it looks 3, but the constraint is 2 only. So, 3 contacts providing 2 constraints only. It means one is redundant, one is extra, which was not necessary, and even if we remove one of them, it does not make any difference, and DOF is still 1 in this case, which is theta z. Here 2 x and y translation. So, what we understand from this design that yes, we can remove any one of them and still we will not have any issue in terms of degrees of freedom and constraint. So, it is over constraint design. So, if we try to impose and try to say that we want to use all the 3, what will happen? So, we need to have very high tolerance part, or they will start fighting because which one should take over, which two constraints should provide the 2 constraint, which is x and y translations. Yes, many times we can say okay, it will be averaged out and all those things, but yes, then in that case we have to know a lot of things. We need to control other parameters, we need to control the dimensions well, and that is why it is very important to know if there is any over constraint and what will be the implications. So, this design is over constraint design. Over constraint. So, take another example. So, I think it is very similar to one of the case we discussed, C 1, C 2, C 3. So, I think this is a straightforward, there are 2 ICs, and so it will constrain x translation, y translation, and if we talk about theta z will be constrained by C 2 and C 3 because they are parallel and with an offset. So, if we try to rotate the 2 constraints C 2 and C 3 with an offset, they always provide rotational constraint, and that way. So, whenever we try to rotate, want to give theta z motion, so C 2 and C 3 they are parallel with an offset. So, they will provide the required constraint and the moment, and therefore, it will not let it rotate. So, in this case again it is a fully constrained, the in 2D for planar case is a fully constrained. So, we have 3 constraint, 3 contacts. So, is exactly constrained and off is 0. So, there will be no motion. Again in this case, whenever we place the object against these 3 posts, it will always go to the same location, and that way the repeatability is always ensured. What will happen in this case? So, I think it is very important to understand the interface. So, whenever we talk about the contact point, first need to identify where is the contact. So, and also let us be little systematic. So, call it post 1, post 2 and post 3. So, many times when we do the analysis, we will also try to label it, so that we know what we are doing. So, post P1, P2, P3, then we have contact C1, C2 and C3, and what we need to identify is the tangent plane. So, of course, the tangents are well defined here at the contact tangent lines. So, they are well defined, and perpendicular to that tangent line passing through the contact point will define the constraint line. So, in this case it is very obvious. So, this is the constraint line. In case of P2, this is the constraint line. In case of P3, we have to find. So, these are the constraint lines. So, again all of these are constraint lines. And this is another one. So, again what we see here is, if we take a pair, we can define ICs, instantaneous centers. So, I see in this case C1 and C2. So, I see 1, 2, and similarly like here 1 and 3. So, I see 1, 3, and this is I see 2, 3. What we also realize that if we extend the constraint lines, and if it encloses an area, so if it forms some kind of triangle, what we can prove and easily see that then there is no over constraint and the system is exactly constrained. So, in this case also, if we analyze, what we can find, x, y and the theta z all constrained. So, we can take any pair. So, for instance, if we take IC 1 and 2 this and try to see, if try to rotate, what will happen. So, if you just consider the 2 constraints C1 and C2, it tends to rotate along an axis passing through IC 1, 2 here, and if we try to do that, what will happen? It will try to move along this line passing through C3, which is the constraint line C3. So, which will not allow any motion, and therefore, the rotation is also not possible. So, all 3 are constrained. So, again fully constrained, 3 contacts, 3 constraints. So, x, y and theta z all constrained and 0 degree of freedom, and 0 degree of freedom is means kinematically clamped. So, likewise we can proceed. So, maybe I will try to ask more, and maybe we will try to explain, come to these examples one by one again. Here again we find that there is a redundancy, C1, C2 and C3. So, out of C1 and C3 they are along the same line. So, again there is over constraint. So, maybe I'll try to know from you, and you do the analysis and try to tell me what is wrong with this and why is over constraint. So, here constraint will be not 3, but 2, there will be 1 over constraint, what will be that? And there will be still 1 degree of freedom, what is that? So, I would like to know from you, and we can come back to these examples later. So, I am leaving it here. Similarly, we have another example. So, we establish the contacts C1, C2, C3, C4, and if we try to make the constraint line, what we realize here, the number of contacts 4, but does not mean it can provide 4 constraints, because in planar case there will be only 3 degrees of freedom. So, you cannot have 4 constraints. It means there is again some kind of over constraint there, over constraint. So, over constraint design, and definitely I would like to know what is something which is over constraint, overly defined. And if we are talking in terms of constraint and degrees of freedom, constraint is, I am saying 3, but so what is the over constraint? Over constraint, and DOF is 0, right. But if we go by this, there are 4 constraints, right. So, 4 contacts and 3 DOF. So, 3 minus 4 equal to minus 1. So, it means what we can also say that there is one over constraint here, and that has to be identified, and possibly we may have to remove it. So, again I am leaving it here. What will happen in this case? So, many examples C1, C2, C3. Again in this case I am not making the constraint lines, and I will come back to this. So, I am leaving this as an exercise and try to know from you what will be the constraints and what will be the degrees of freedom. This is also homework. Homework for you. Yes, so another interesting thing is the nesting force, what we have been mentioning all the time. And what we also realize that simply placing a fourth post does not solve the purpose. So, what he says, a fourth post is over constrained and does not replace the nesting force, because if you try to get that nesting force by using another post, what will happen? It has to be very exact. So, what will happen? We have to control the dimensions really well here, and so either 2 things can happen. Either there will be interference, so it will be pressing the part, or there will be loose contact, there will be gap here. So, either no contact or interference, both is not good, and it cannot provide sufficient nesting force. So, therefore, this is a bad idea to use another contact to just get the nesting force. So, there are various ways to get the nesting force. One is the gravity itself, because of the weight you can get. So, if that is the case, and C1, C2 and C3 one can analyze how. So, we will take up this problem one by one later. Another very good example is eccentric cam. So, in bicycles, in many of these products these days. So, you use either a oblique object or elliptical object, and or even a circular object and then slightly offset. So, whenever you rotate, the radius, the distance is different, and that is why it is very easy to clamp. So, moment you rotate it, you can clamp it, and you can provide, just by rotating you can provide the sufficient nesting force. Many times, I think very good example is spring or some kind of compliance, and this is something I think many times advised, because you just put the spring and torque it, or put the enough extension or compression, and you can provide enough force. So, that then you can make all the contacts. Also through the screw, if you turn, you can press and provide the nesting force. So, there are many ways. You can also say you can use magnets for the same purpose. So, that is also possible, and many times it is also used. So, nesting force, where to apply, how to apply, I think is one of the topic we will consider in the coming lectures, and what we try to learn, that there is a nesting window, nesting force window possible. It is not just one force, but like one area defined. So, if you are able to find the nesting force window, we have many choices. It may happen in some cases we do not have that, and then we realize that is unstable and we may not be able to provide enough constraint. So, we will talk about these things in the coming lectures. Thank you.